Chapter 3, Logic Gates. Now that we've had a look at binary number systems, let's put them to work in a practical application. Gates. Gates are used in everyday intelligent electrical devices, or IEDs, such as computers, microprocessors, smart house devices, metering, and relays, just to mention a few. We looked at binary numbers because they are the root to binary quantities, binary variables, and binary systems. A binary quantity is one that can take only two states. This is a binary arrangement with a switch in series with a power source and a light. The switch can be open or closed. The light can either be on or off. We can now assign a binary number to the switch and to the light. For the light, on would be 1, off would be 0. For the switch, closed would be the equivalent of 1, open would be the equivalent of 0. And in order to analyze these binary arrangements, we devised a truth table. And the truth table has an output for every possible input. So the switch can either be open or closed, can be 1 or 0, and the light would either be on or off, signified by a 1 or a 0. This is a binary arrangement that has two switches in series with a power source and a light. Either switch can be open or closed. The light will either be on or off. And as before, we can now assign a binary number to the light and the switch. For the light, on is 1, off is 0. For the switches, closed is 1, open is 0. And in order to analyze the binary arrangement, we have devised a truth table. The two switches form what is known in logic terms or in gate terms as an AND gate. We state that the light will be on, or the L is equal to S1 and S2. In other words, the light is on with when both switch 1 and switch 2 are on. And the truth table displays this, where you have zeros if either of the switches are off, but if both switches S1 and S2 are on, then you have a 1 for the light. Here is another binary arrangement with two switches, this time in parallel, which generates this truth table. When either of the switches are closed, or a 1, then the light will be on, or 1. It requires both switches to be open, or 0, in order for the light to be off. The two switches form what is known in logic terms as an OR gate. We state that the light, in order for the light to be on, S1 or S2 have to be 1 or closed. Here is yet another binary arrangement, this time with three switches in series, which generates this truth table. The three switches form what is known in logic terms as an AND gate, and we state that L, in order for L to be 1, S1 and S2 and S3 have to be closed. So all three switches have to be a 1. If any of the switches are a 0, the output is 0, or the light is off. Of course, we have to look at the parallel arrangement of the switches as well. And this generates the following truth table. The three switches form what is known in logic terms as an OR gate. And we state that the light, in order for it to be on, S1 or S2 or S3 have to be on or closed. Looking at the truth table, it is stating the same thing. If any of the switches are closed, you will get a 1. In order for the light not to be on, all of the switches have to be open. One more example before pressing on to other matters. We have a 3-switch arrangement, this time a combination of a series parallel arrangement of the switches. This circuit would generate this truth table. The logic of these three switches can only be described by the equation L, and L is 1, or the light is on, if switch S1 and either S2 or S3 are closed. And the truth table demonstrates this as well. If all of the switches are 1, of course you get a 1. If any one of S1 or S2 is closed and then S1 has to be closed as well, you would get a 1. If S1 is open or 0, then you're going to get a 0. And if both S2 and S3 are open, then you also get a 0. Mechanical switches are really good for demonstrating the logic arrangement of switches and lights. However, in most solid state systems, computers, etc., the logic is set up in terms of voltage levels. A 0 volt or a low logic level is a 0. 5 volts is equal to a high or a logic level of 1. In this transistor circuit arrangement here, the transistor is in a state of saturation by virtue of the applied input voltage, the 5 volts, through a 2-position switch. Because it is saturated, the transistor drops very little voltage between the collector and the emitter, resulting in an output voltage of practically 0 volts. If we are using this circuit to represent binary bits, we would say that the input signal is a binary 1 and the output signal is a binary 0. Any voltage close to full supply voltage, measured in reference to ground, of course, is considered a 1, and a lack of voltage is considered a 0. Alternative terms for these voltage levels are a high, the same as a binary 1, and a low, the same as a binary 0. A general term for the representation of a binary bit by a circuit voltage is logic level. Moving a switch to the other position, we apply a binary 0 to the input and receive a binary 1 at the output, putting the transistor into cutoff. What we've created here with a single transistor is a circuit generally known as a solid-state logic gate, or simply a gate. A gate is a special type of amplifier circuit designed to accept and generate voltage signals corresponding to binary 1s and 0s. As such, gates are not intended to be used for amplifying analog signals. Used together, multiple gates may be applied to the task of binary number storage, memory circuits, or the manipulation, computing circuits. Each gate's output representing one bit of a multi-bit binary number. Just how this is done is the subject of further study. Right now, it's important to focus on the operation of these individual gates. The gate shown here with a single transistor is known as an inverter or a NOT gate because the output is the exact opposite from what is on the input. For convenience, gate circuits are generally represented by their own symbols rather than by their circuit diagrams of transistors and resistors. Logic gates are the building blocks used to create digital circuits. There are 3 elementary logic gates and a range of other simple gates. You'll see these shortly. Each gate has its own logic symbol, which allows complex functions to be represented by a logic diagram. The function of each gate can be represented by a truth table, and that truth table is unique. Looking back very quickly at the single transistor switching circuit that provided us with the logic of what is called an inverter or a NOT gate, rather than drawing out a network of switches and or transistors, gate symbols are used in conjunction with their logic truth tables to symbolize logic functions. This is the symbol for an inverter or a NOT gate. The logic is described by its truth table. It has one input and one output. The output is the complete reverse of the input. In other words, a 0 on the input provides a 1 on the output. A 1 on the input provides a 0 on the output. Remember our series switched circuit. We can now represent this system by the standard 2 input AND gate symbol with its truth table, which is identical to the 2 series switch version. Reading the truth table, if A and B are 0, you have a 0 output. If one of the inputs is 0, you have a 0 output. You need both inputs to be a 1 to have a 1 on the output. Then we can remember our 3 switches in series. We can now represent this system by the standard 3 input AND gate symbol with the truth table, which describes how that AND gate works. And how it works is you need all of the inputs to be a 1, otherwise you would have a 0 on the output. That agrees with the same truth table we used in our mechanical switches. What this truth table means in practical terms is shown in the following sequence of illustrations, with a 2 input AND gate subjected to all possibilities of input logic levels. An LED, a light emitting diode, provides the visual indication of the output logic level. So with zeros on the input, the output is 0. In other words, the LED is not lit. If you switch A to have a high input, we still don't have high on the output. In other words, the light emitting diode is not lit. If we switch the B input to a high level, or a 1, we still don't get an output. However, if we switch both A and B high, then the AND gate gives us the logic level 1 output, which will light the light emitting diode. So let's have a look at that just to repeat it so we can see how it works and cement it into our memory. If we change the input A from 0 to 1, nothing happens. If we change the input B to 1, nothing happens. However, if we change both inputs to a 1, the output gives us a logic level 1 and lights the light emitting diode. A variation on the idea of an AND gate is called a NAND gate. The word NAND is a verbal contraction of the words not and and. Essentially, a NAND gate behaves the same as an AND gate with a NOT or an inverter gate connected to the output terminal. To symbolize this output signal inversion, the NAND gate symbol has a bubble on the output, which differentiates it from a simple AND gate. The truth table for a NAND gate is, as one might expect, exactly the inverse as that of an AND gate. As with an AND gate, NAND gates are made with more than one input sometimes. In such cases, the same general principle applies. The output will be low or a 0 if and only if all the inputs are high, a 1. If any of the inputs are low, a 0, the output will go high, it'll be a 1. Our next gate to investigate is the OR gate. They can have any number of inputs. For example, this one has 2 inputs, an A and a B input, and the OR gate is symbolized like this. It can also have multiple inputs, and this one is indicating 3 inputs, A, B, and C, and the symbol is the same, it just has more inputs. The truth table for each are depicted here. So-called an OR gate because the output will be high, a 1, if any of the inputs are high, or a 1. The output will be low, 0, if and only if all of the inputs are low, or a 0. So let's hook up our OR gate now to our light emitting diode, and the following sequence of illustrations demonstrates the OR gate's function with the 2 inputs experiencing all possible logic levels. LED, or a light emitting diode, provides the visual indication of the gate's output logic level. So if we switch 1 from a low to a high, or A from a low to a high, the light emitting diode will light. In other words, a 1 on the A input will give us a 1 on the output. If we switch B to a 1 and switch A to a 0, we still get the light emitting diode to light. And if we switch both of them to a 1, again we get the same result. The output is a logic level 1 and the light emitting diode will light. So let's repeat that just to have a second look at it. If any of the inputs are 1, you get an output that'll light the light emitting diode. As you might have suspected, there exists an inverted OR gate known as a NOR gate, which is an OR gate with its output inverted. You'll notice that there's a differentiation between the OR gate and the NOR gate by the placement of a little bubble on the output of an OR gate, which symbolizes it to be a NOR gate. NOR gates like all other multiple input gates seen thus far, can be manufactured with more than just two inputs. Still, the same logic applies. The output goes low, 0, if any of the inputs are made high, a 1. The output is high, 1, only when all of the inputs are low, 0. Another gated function is the negative AND gate. The negative AND gate functions the same as an AND gate with all of its inputs inverted, connected through NOT gates. In keeping with standard gate symbolization convention, these inverted inputs are signified by little bubbles on the input. Contrary to most people's first instinct, the logical behavior of a negative AND gate is not the same as an AND gate. Its truth table actually is identical to a NOR gate. The output goes low, 0, if any of the inputs are made high, 1. The output is high, 1, only when all of the inputs are low, 0. Following the same pattern, a negative OR gate functions the same as an OR gate with all of its inputs inverted. In keeping with standard gate symbol convention, these inverted inputs are signified by bubbles. This function can also be written as these equivalent gate circuits. The behavior and truth table of a negative OR gate is the same as an NAND gate. The exclusive OR gate. The last 6 gate types are fairly direct variations of 3 basic functions, AND, OR, and NOT. The exclusive OR gate, however, is something quite different. The exclusive OR gate's output is a high 1 logic level if the inputs are at a different logic level. They're either going to be 0, 1 or 1 and 0 on the input. Conversely, the output is a low, a 0 logic level if the inputs are at the same logic level. The exclusive OR is sometimes called an XOR gate, has both a symbol and a truth table pattern that is unique. There are equivalent circuits for an exclusive OR gate made up of AND, OR, and NOT gates, just as there were for NAND, NOR, and negative input gates. A rather direct approach to simulating an exclusive OR gate is to start with a regular OR gate, then add additional gates that in combinations work like this. If A and B are the same, both 1s or both 0s, the both AND gates output will be 0, making the output of the OR gate 0. If A and B are different, 1 and 0, one of the two AND gates output will be 1, making the output of the OR gate 1. Thus, the truth table holds true for this combination of gates, meaning we can replace them with the exclusive OR gate. Exclusive OR gates are very useful circuits where 2 or more binary numbers are to be compared bit for bit, and also for error detection or parity checks and code conversions. Finally, our last gate for analysis is the exclusive NOR gate, otherwise known as a NEX-NOR gate. It is equivalent to an exclusive OR gate with an inverted output. The truth table for this gate is exactly opposite to that of an exclusive OR gate. As indicated by the truth table, the purpose of an exclusive